In the last class, we had discussed about the overall propulsion mechanism, what is the key aspect related to this propulsion mechanism. We had discussed about the varying modes of propulsion mechanism in detail. In today's lecture, we will take up a case study, basically an AFM, which is called as a atomic force microscope. So, the main this is considered to be one of the characterization tool for studying the surface characteristics or the surface behavior. So, this tool is considered to be a kind of a micro and nano robot, okay, because of its functionality as well as because of its application. So, let us take that as an example and let us see some of the key characteristics. In fact, we will discuss in detail about the overall mechanism which had been deployed with reference to this atomic force microscope. In fact, during our introductory slide also I had discussed that micro robots has a potential application in the material characterization perspective point of view, especially because of its micro manipulation. It has a wide spectrum towards material characterization. Here also with reference to atomic force microscopic perspective point of view, the manipulation behavior has a good impact, okay. So, with reference to the micro robotic related applications. Now, before going into the lecture, so we will discuss about the key constructions of this atomic force microscope. So, as far as when we closely observe the different components which are involved in it, is one of the major component which participates towards surface integrity is the cantilever, and then there is a kind of a laser source and then the photodiode which is available. So, this laser source, the light from the laser source is made to incident on the AFM and it is reflected back on a photodiode. From the photodiode, it measures the reflection and then there is a feedback circuit which is available, which goes to the display. Now, in this particular system, so we have a kind of a piezo scanner which exhibits over here. Over the piezo scanner, there is going to be a sample, okay, so which requires a kind of a characterization. So, ideally the main motto is to study the overall surface integrity, or the main motto is to study the overall surface waviness or the surface roughness. So, we have a sample surface in place and then there is a cantilever beam which is available with an AFM tip. So, the incident beam is made to incident on the cantilever beam. The cantilever beam is made to trace the profile of the sample surface. Now, the waviness in the cantilever beam is continuously monitored using a reflected beam, and the overall deviation which is happening on the sample surface is measured using a kind of a piezo scanner which is available. So, this piezo scanner will be helpful for measuring the overall waviness, or like a piezo scanner is mainly meant for manipulating the sample based on the cantilever motion, okay. So, that is the reason the overall motion of the cantilever beam is recorded using a photodiode, it is sensed using a photodiode, and the feedback gets two signals. So, one is from the piezo sensor and the other one is from the photodiode. So, that is how, so both are getting interface and appropriately the control strategies are being deployed into it. Now, in order to look into the fundamental of this particular atomic force, first point is as far as in this particular case is concerned, the cantilever is considered to be a kind of a micro manipulating element. Since the cantilever has a very narrow tip, ideally in the order of few nanometers, it has a kind of a contact and a non-contact based micro manipulation which exhibits over here. Of course, we will discuss in detail how these contact and non-contact based micro manipulations are efficiently participating towards the material characterization. For that, we need to have a certain amount of fundamentals with reference to the overall micro manipulation of this AFM tip. Now, as far as in this when we try to look into the construction and working, ideally when we try to talk about the overall cantilever with the atomic force microscope tip, the cantilever is a kind of a micro machined beam which is ideally made out of a silicon or a silicon nitride. Its stiffness has to be much smaller than its spring constant for a better resolution. Now, when we try to look into the spring constant and the resonant frequency of the cantilever are represented as K, which is like depends upon the parameter E, which is the Young's modulus of the material. So, ideally here we are using a silicon nitride. So, the value for silicon nitride is 1.5 into 10 power 11 Newton per meter square, and then it also depends upon the length, width and thickness of the cantilever beam respectively. So, the overall equation for measuring the spring constant, for estimating the spring constant and the resonant frequency is K equals E T cube B by 4 L cube. And now, like, so this is going to be the spring constant, and when we try to measure the frequency, so here the frequency is represented by 1.8751 square by 2 pi T by L square root of E by 12 rho. So, rho corresponds to the density of the cantilever material. Since low value of stiffness is advantageous for measurement of soft material, we may need to reach a kind of low value as possible, and then while measuring in the liquid environment there is a fundamental limitation in lowering the K. So, these are some of the key challenges which needs to be addressed. Now, when we try to closely observe the cantilever with the AFM tip, the cantilever is in a thermodynamic equilibrium with a thermal bath at a temperature T and has a thermal energy which we can represent it as KBT. KB is the Boltzmann's constant. So, let us consider a 1 degree of freedom cantilever which has only a vertical motion, and the thermal energy increases the elastic energy stored in the cantilever. So, ideally when we try to equate the thermal energy and the overall thermodynamic equilibrium, so half K A squared equals half K B T, where when we try to calculate the A, which is nothing but the A is the oscillation amplitude of the cantilever, which is root of K B T by K. So, these soft cantilevers are used in contact mode to avoid damage to the samples, and stiff cantilevers are used in a dynamic mode for appropriate operations. Now, when we try to look into the calibration of this system, so the mass of the cantilever is distributed uniformly throughout the length for calibration, and its effective mass m0 is considered. In the method suggested by from the researchers, the change in the resonant frequency f of the cantilever were measured as a small addition of mass. So, omega squared equals k by m star plus m naught and f equals omega by 2 pi. So, for accurate dimension of the cantilever, the spring constant is given by k equals 2b pi Lf cube by rho cube by E. So, L and B are the length and width of the cantilever, rho is the density of the material, E is the Young's modulus and F is the measure of the resonant frequency. Now, when we look into the cantilever dynamics in a liquid, so when we try to when we need to consider the overall dynamics of a cantilever in a liquid, the spring constants depends only on the material properties, but the viscosity of the surrounding medium affect the mechanical responses. So, let us consider the cantilever is dipped in a liquid and inside we have a waviness. The liquid reduces the resonant frequency of the cantilever. So, the movement of the cantilever driven by an externally oscillatory force F t equals F naught cos omega t, which is derived by the equation m equals d squared as z by dt square plus k dz by dt plus gamma z, which is equals F naught cos omega t. So, z is the vertical displacement of the cantilever, m is the mass of the cantilever, F naught is the amplitude of the oscillating force, and gamma is considered to be the damping coefficient which exists. And then the overall governing equation is represented when we consider the cantilever is working in the kind of a liquid medium. Now, when further extending, so gamma is m omega naught by q. So, omega naught is the free vacuum resonant frequency and omega r is the omega r is the resonant frequency in fluid. Q is the quality factor. So, when we try to consider is gamma equals m omega naught by q and omega r equals omega naught root of 1 minus 1 by 2 q square. So, the solution of the differential equation is z equals b exponential minus alpha t cos omega r t plus beta plus a cos omega t plus phi. After time t equals 1 by alpha 2 q by omega naught, the transient term diminishes and the motion tip is dominated by a steady state term only. So, and the amplitude a omega and the phase lag phi can be calculated by the equation a omega equals f naught by m omega, that is root of omega naught square minus omega square by the whole square plus omega naught by q the square, and the tan phi is represented as omega naught by q and omega naught square minus omega square. Now, when we see this construction, so in this construction we have a photodiode in place. How photodiode participates and what kind of impact does it has on the system, let us discuss in detail. So, as far as these photodiodes are concerned, these photodiodes are the detectors which measures the deflection, the reflected beam from the cantilever. It provides the data for position of the cantilever with respect to its original position. So, these photodiodes are made of four quadrants. So, let us consider to measure the overall least spot position as well as the direction. So, these are considered to be the 4 quadrants of the photodiode. So, when we consider a kind of a vertical deflection comparing the signal from top and bottom halves of the detector, it is meant for measuring the interaction force, and then there is a kind of a lateral twisting which exists. So, as far as in this lateral twisting is concerned, it is used for comparing the signal from the left and right halves. So, when we consider the vertical deflection signals, we have the A plus B plus minus C plus D as a ratio of A plus B plus C plus D. So, ideally, so this will act as a kind of a mechanism to investigate the overall reflected signal which is coming out of the cantilever. Now, let us talk about the piezo scanners. As far as these piezo scanners are concerned, so we have discussed a lot about these piezo scanners. So, these piezo scanners are ideally a kind of a piezoelectric transducer which is used for accurately positioning the tip and the sample with a sub-nanometer precision. So, they are highly sensitive, stable and reliable. The application of external voltage induces a reverse piezoelectric effect in the scanner which results in change in its dimension. Generally these for such kind of AFM related applications, so a kind of tube scanners are used. So, as far as these tube scanners are concerned, so these are kind of stacked piezoelectric structures which exhibits. So, ideally, so we can have a kind of a manipulation in z direction as well as we can also have a manipulation in x direction and we can also have a manipulation in y direction. So, appropriately the samples are mounted and the overall manipulation of the sample will have an impact on the structure. Now, let us discuss about the different principles which are being deployed with reference to this cantilever perspective point of view. So, in the case of this cantilever, so as we have seen here, like the cantilever is made to trace the profile and appropriately we try to get a signal coming out of it. So, there are two different mechanisms which exhibits, like two different kinds of modes which exhibits. Like in this mode, one mode is a kind of a motion up and the other one is kind of a down along the surface roughness. So, that is if we have a kind of a waviness over here and when the cantilever is made to move along the waviness, so appropriately we will be getting a deflection from this particular point. So, whatever waviness which the cantilever is tracing, that will be efficiently recorded by the photodiode. So, ideally the scanning of the sample surface with the sharp tip, ideally here we call it as a probe or the kind of a cantilever, which basically depends upon the force between the tip and the sample surface. So, when the AFM tip is brought in close proximity of the sample surface, the force between the tip and the sample surface lead to the deflection of the cantilever, which is basically governed by the Hooke's law. So, most of us are aware about the Hooke's law. So, the motion of the cantilever is captured and amplified to generate the image of the surface. So, ideally the AFM works in two different modes. So, one mode we call it as a force mode and another one is called as a distance curve mode. So, let us discuss about this force mode and the distance curve mode. So, when we try to plot a graph with reference to this force mode versus the distance curve mode. So, in the case of a force mode, so if I try to plot a graph with reference to the force and the sample to a dip distance, so there are three different regions which exhibits. One is called as a intermittent contact, another one is called as a contact region, another one is called as a non-contact region and the sample to tip distance. So, it is the plot is between force versus sample to tip distance. So, we have two different domains which exhibits. One is a kind of a repulsion domain and the other one is kind of an attraction domain. So, when the sample to tip distance is high, that is in the region beyond point A, no interaction happens between the sample and the tip. However, the distance is reduced and it comes in the range of A and B, which is called as a non-contact region. Due to more distance, the attractive forces are dominant between the tip and surface and this region is called as a non-contact AFM. If the distance is in the region of C and D, the repulsion force are dominant and the region is used for a contact based AFM. So, both the regions will be utilized for simultaneous for intermittent mode, which we call it as a kind of a tapping mode. So, that is both the contact mode and that is the contact region plus the non-contact region will be utilized when the AFM is in the tapping mode. Now, let us see some of the key principles which exhibits. Now, let us consider a tip motion when a tip is approaching. So, it is the tip to the surface distance is in the range of 10 to 100 micron and that when the tip is approaching. So, the overall distance is getting reduced to few micron and when it is close to the surface. So, we have a kind of a distance in the order of nanometers to atomic distance. Now, when it is far away, of course, when we try to look into the interaction perspective point of view, there is no interaction which exhibits over there. When the tip approaching, there is going to be a repulsion, which is a kind of an electrostatic force which exhibits. When the tip is closer to the surface, basically in the order of nanometers to atomic distance. So, the repulsion which will result in a kind of a van der Waals forces, a capillary forces which is in air, then a chemical potential and a magnetic force which exhibits. Now, with reference to contact perspective point of view, there is going to be a tip touching sample and then interaction perspective point of view, a material stiffness and a viscoelastic response which exhibits. Now, let us talk about the tip retracting phenomenon. So, in the case of a tip retracting phenomenon, so in the case of a tip approaching, it is going to be something like this. This is the point at which tip is in contact with the surface. So, this is a kind of a tip retracting phenomenon, that is there is going to be a waviness which exists because of the movement. So, there are three different like motions which can be monitored. So, one is a kind of a lifting off, basically a kind of a few atomic distances 2 nanometers, a tip further away which a kind of a nanometer which exists, tip far from the surface which is in the order of 1 to 5 microns. Now, when during the lift off, when there is a few atomic distance to nanometer is there, there is going to be an addition which will result in a kind of a chemical affinity, a surface coating and a self surface interaction. Now, with respect to tip farther away, ideally in the order of few nanometers, we have a addition in place, and then there is going to be a stiffness, and then there is going to be a kind of a structural transition which exhibits. When tip is far from the surface, so ideally there is no much interaction is observed over here. So, now when we try to look into the overall force detection method of for imaging, so like let us take this laser beam deflection method. So, in this laser beam deflection method, let me just introduce you. So, here we have the cantilever, the moment of the cantilever is marked as Z, and then this is going to be the photodiode and this is going to be a laser source, and the force exerted is marked as F, which is measured over here, and then a laser is made to interact on the cantilever. So, ideally like when it is in position A, this will be the reflected signal, and when it is in position B, we get a reflected signal. So, consider the AFM tip has moved away from the sample by a distance Z in a vertical direction. This is due to the repulsive vertical force F between the sample and the tip. So, the reflected laser beam from the cantilever is deflected by an angle theta, which is represented over here. So, angle at the end of the cantilever in the presence of force F is estimated as, let us consider if theta equals FL square by 2 EI. So, where E is considered to be the Young's modulus, I is considered to be the moment of inertia. So, this is a kind of a laser beam deflection method. Now, when we want to measure the force detection method for imaging with reference to this laser beam deflection method. So, for a rectangular cantilever, let us consider the E and I, which is equal to KL cube by 3. So, K is a kind of a spring constant fulfilling L in the cantilever length, which can be represented as F equals KZ. For small displacement of the tip, let us consider theta equals 3Z by 2L. So, tan theta equals D by S. So, the amplitude displacement of the cantilever is D equals 3 SZ by 2L. So, the accuracy of the beam deflection method can be high as 0.1 Armstrong, and it is limited to a random thermal excitation of the cantilever. Now, let us consider a kind of a piezoelectric cantilever and a tuning fork. So, here, so in this particular case, so when we try to introduce, so we have a piezo scanner and then there is a sample, there is a piezoelectric layer over here which acts as a kind of a piezoelectric cantilever, and then there is going to be a kind of a AC driving signal which is being fed over here. So, the deflection from the piezo layer is measured from the deflection sensing electronics, and then there is a feedback loop which exists. From this feedback loop, the feedback is fed into the piezo scanner. So, that is based on the deflection of these piezo layers, appropriately a signal is fed into the piezo scanner and the movement of piezo scanners are monitored. So, the piezoelectric thin film is coated on the cantilever beam. Bending on the cantilever beam stresses and deform the piezoelectric layer. So, due to a direct piezoelectric effect, a voltage is generated in the piezoelectric layer with amplifier circuit which can obtain the voltage proportional to the cantilever deflection. So, this piezoelectric layer is also useful in providing oscillation to the cantilever by applying an external AC field to it through this AC driving signal. So, through this AC driving signal, there is going to be a kind of a mode which exhibits and the piezoelectric thin film moves appropriately. Now, like what happens is, so when we have a kind of a tuning fork, so the AFM tip is glued to one end of a small quartz tuning fork. The force is forced to oscillate and then a damping. So, when we try to look into the overall configuration of it, so this is a kind of a fork which is being integrated with a kind of a cantilever. Then there is going to be a small AC driving signal, and then there is an oscillator with sensing electronics and a feedback loop in place. From the feedback loop is fed into the piezo scanner, and then there is a sample which is available. So, this method is called as a tuning fork method. So, like here, as and when once there is going to be a deflection in the cantilever, of course, the fork is going to exert a kind of force to oscillate it. So, the damping of amplitude of oscillation due to tip sample interaction is monitored. The force resolution is generally in the order of 0.1. So, the probe do not touch the sample employed for this non-contact phase AFM. Okay. So, here the overall feedback is monitored from the piezo scanner as well as from the sample. Now, let us discuss about the two different modes of operation which exhibits. One mode is called as a contact mode. So, as far as in this contact mode is concerned, so the tip never leaves the surface, it is used for a very high resolution imaging. So, like for example, you have a sample and the tip will try to move, or it will try to trace the sample, so that we can continuously see the waviness in the system. There is a maximum vertical forces there, which is used for control to minimize the compression of the sample. The fast scanning are good enough for measuring the surface roughness. Sometime if it is a soft sample, it may damage the sample, or if it is done in measurement is done in air. So, this is one of the major limitation or risk which is being deployed in the case of a contact mode is concerned. So, sometime what happens is this lateral force may sometime distort the image also. So, this is one important aspect which we may need to look into it. Next mode is called as a tapping mode. So, as far as this tapping mode is concerned, like tip is not in contact with the surface for most of the oscillation cycle. It is used for imaging the samples which are not firmly struck on the surface, such as molecules. So, the cantilever is driven close to the resonance of the system to give an amplitude for oscillation, and the cantilever oscillates and tips makes a kind of a repulsive contact with the surface at the lowest point of the oscillation. So, the oscillation can be achieved with a small piezo element in a cantilever holder and a AC magnetic field or a piezoelectric cantilever, or periodic heating with a laser beam. So, these are some of the kinds of modes or the oscillations which can be achieved. So, and the imaging forces are lower. So, this is one configuration with reference to the tapping mode. And then when we try to talk about this FM AFM, so that is a kind of a force modulation mode. So, the tip does not leave the surface, but makes a small oscillation. This dynamic form of contact mode is called as a kind of a force modulation which is available, and the cantilever is kept oscillating within the fixed amplitude at its resonant frequency, and the image is formed by the constant frequency shift between the current frequency and the free resonating frequency. So, we will discuss about this non-contact mode and the other feedback related modes in the upcoming classes.